Hi, welcome to stage 2 of Chump, a homemade processor. In this stage, we've added the control ROM. There are also 2 EEPROMs to decode the output of the control ROM into 2 hexadecimal 7-segment displays. Currently, the machine is going through a sample program, but if we set the program counter to 0 and first switch it to the page containing the other sample program, we can single step through the program, demonstrating that it does indeed work. So here's a written out version of what the program should contain, and now let's verify it. So address 0, which is what it's currently on, as we can see from these LEDs here, it has machine code hex 82, that's correct. Address 1 should have hex 10, that's correct. Address 2, hex 21, address 3, hex 62, address 4, hex A0, and then address 5 all the way to the end of the page will be blank, which is just FF, because these EEPROMs come with 1s written in. Eventually this is going to be corrected because the control ROM will create what's called a branching instruction, and when it gets to hex A00, that is the assembly language code go to 0. So it'll skip back and it'll go to address 0 and it'll repeat these 5 lines. But for now, it's just going to cycle through these lines until it gets back to 0 from overflowing. As there were many EEPROMs involved in this section of the build, an EEPROM programmer was necessary. So this circuit uses an Arduino Nano in order to burn an EEPROM, and it uses 2 shift registers to extend input and output capability. Essentially the way it works, it sets the address pins on the EEPROM using the shift registers, then it puts the desired data on the I/O pins and sends a pulse to the right enable pin. Now that's greatly simplified, but there's a great video from Ben Eater on how it works, so I'm not going to get into it too much, as I'd rather talk about how the EEPROMs work in the context of Chump. So let's talk about how this fits into the Chump build. Essentially, the program ROM has its inputs tied to the program counter. This is how each clock cycle goes to a new line of the program. The program ROM contains an 8-bit control code for each line of the program. The high nibble of this is the opcode, or instruction for the computer to execute, and this pertains to a specific action in assembly language. Each assembly language action has 2 opcodes, one for its constant flavor and one for its memory flavor. The constant flavor executes the instruction using the data provided in the low nibble, whereas the memory flavor executes the instruction using data from memory. In a future stage, the opcodes will be fed into another EEPROM called the control ROM, and this ROM converts the opcode into control signals that interface with the rest of Chump, and this allows it to perform the basic functions it does, such as addition and subtraction. Thank you so much for watching this video, and I will see you in the next stage.